Hey, and we're back on example 5. The graph of a function is given. Make a rough sketch of an antiderivative capital F given that capital F of 0 is equal to 2. You might read this and go, I have no idea what she's talking about. And you know, that's what, when I first looked at this, I thought it can be confusing, but you have to apply things that you already know. This, remember, f of x is capital F prime of x. So that means this is the slope graph. This is the slope graph for f. So if you think about that, oh, it kind of looks sloppy. I'm going to fix that. Okay, so this is, you're going to think about as the slope graph. So, so you're going to go, ooh, this f, capital F prime is the slope of f. So first thing I'm going to do is start out with information that I know about, that I'm pretty sure, convinced that I've got something to start with. So number one, I'm using this information that capital F of 0 on the antiderivative graph is 2. That gives me at least the point, right, 0, 2. I'm going to scroll down just a little bit, and I'm going to put that on the graph right here. Ooh, it looks like it's already snuck in there. But that's the point 0, 2. That gives us an initial condition where we're going to start. Okay, now the second thing is I'm going to have to recognize and get really tight with this fact that if f is equal to f prime, if f is negative, so is f prime. That means that capital F, the antiderivative, is decreasing. I'm going to abbreviate decreasing. So if f is negative, f is decreasing. If f is positive, you know, you might be thinking about what does she mean by that? And we'll get to that in 1 second. But if f is positive, that means f prime is positive. Capital F prime is positive. So that means f is increasing. We talked a lot about this when we found mins and maxes. So what are we talking about? Let me get a couple different colors here. Let's go red. So I'm going to put red below the axis. I'm going to color the graph. I have to change the style of the pen a little bit. So red below the axis, and then I'm going to color green above the axis. Colors don't mean anything. And then I'm going to make some points on the axis. I'm going to put a point here. Ooh, that's where it crosses the x-axis. So, and then I'm going to make a couple notes about this. I need a thinner pen. Here we go. Boom. All right, so if f is negative, then f is decreasing. Well, if you look down here, let me color code this. So instead of a blue underline, I'm going to say f is negative. So underneath, if the function f is underneath the x-axis, then f is negative and f is decreasing. So we know on an interval that f is decreasing, and we'll talk more about that. So it looks like 0 to 1, it's decreasing, it being f, capital F, the antiderivative. And we also note that from 3 to infinity, it appears to be a decreasing function. However, we're going to look on the top where f is positive. We're going to say, from 1 to 3, it looks like it's increasing. I'm going to put a capital I. I'm going to put a D by these two just as a reminder. Capital F is decreasing, and capital F is decreasing. Remember, if you remember before, we took these graphs and we really messed them up. Okay, so it's increasing on this interval, capital F, that is. Okay, so now let's go to the third bullet. Something happens at 4. Remember, you had to, I'm going to stick with this pen, 3. So something happens at 1 and 3. So it looks like f of 1 is equal to f of 3. They're equal to 0. They're the x-intercepts of f. Recall what this means then. This means that f prime of 1 is equal to capital F prime of 3 is equal to 0 also. So that means you have some horizontal tangents, right? That means we have horizontal tangents. If you look at the graph, and let's mark it up again, where here the graph goes from decreasing to increasing. Now think about this, decreasing to increasing, then that means that this point at 1 where the graph is continuous is a minimum value. In fact, a local minimum value. And then where the graph is increasing and it crosses over to at capital F being decreasing. Now get this, that we're talking about the slope. So where the slope is positive up here in the green area, then when the slope is positive, then that means our function, capital F of x, is increasing. So it's going to go from an increasing to a decreasing at 3. That means at 3, we have a local maximum value. So let me write that over here. So at 1, we have a local minimum. And at 3, we have a local max. So we know we have horizontal tangents, and I'm going to leave that out. So let's move on. We know, if you want to put horizontal tangents, or abbreviate horizontal tangents. Okay, so we know we have horizontal tangents. For number 4 of the information we're going to find, we have, okay, now look what happens to the graph. The limit as x approaches infinity of f of x is equal to 0. So remember, f is the function, and you can kind of see it come around here where you're going, whoop, it's coming up, and you can assume that that will continue unless otherwise noted. So we know that the limit is equal to 0. Therefore, then we know something about the slope. We know that that's equal to the limit as x approaches infinity of f prime of x. That also has to be 0. So we know that f of x gets flat, or at least flatter. Flatter. Don't flatter me. Okay, so that's 4. Now 5, let's see, 5, how much room do I have here? 5. For 5, we're going to take a look at the second derivative. So let's look at the fact, what is f double prime equal to? Well, let me reverse this. If f is equal to f prime, then what is f prime equal to but f, capital F, double prime? Too many f's. All right? So then notice something, that what is f prime of 2 equal to? F prime of 2 is equal to f prime of 4, which is equal to 0. Go back up and look at the graph so we can see this. Let's get some highlighter on this. Let's go blue highlighter here. So let's look at the graph here. You can see here is at 2, here's a 4. We have horizontal tangents on the graph of f. So that means that f prime the slope of f, lowercase f, is equal to the second derivative. Slowing. There we go. That these are equal to each other. The slope of the f graph, lowercase f, is equal to the second derivative of the capital F graph, or the antiderivative graph. So let's write this down now. We've got, these are equal to 0, so then capital F double prime of 2 is equal to capital F double prime of 4. And we haven't drawn the graph, but we know that the second derivative has to be equal to 0 also. So we know on a number line, I'm going to stretch this down just a little bit. Let's do a number line, and let's put the critical numbers 2 and 4 on the number line. And we're going to talk about, on the top, we're going to talk about f prime. That's the slope of the original graph. And remember that that's f, capital F, double prime. And that's going to speak about the concavity. What we're looking at right now is the concavity of capital F and possible POIs, points of inflection. So what we're going to do is we're going to have to look at the slope of the original graph, and we're going to look at test points here, just looking at the graph. We don't need a number line. Keep in mind we start at 0. So that's the beginning of the interval, but we're going to use 1 and look at the slope of 1. We're going to look at the slope of 3, and we're going to look at the slope of, let's pick a happy number, 5. Okay, so going back up to the graph, we want the slope of 1. Clearly, the slope at 1, that works better. Okay, here's 1. Can you see the slope is positive? And the slope at 3 is negative. And the slope at 5 is, this is 5 here, is clearly positive. So your slope is going to go from a positive to a negative to a positive on the interval of f. Go back down here. So positive slope to a negative slope. Remember, we're talking about f prime, capital F double prime. So, and then it goes back to a positive slope. So in this case, we see a definite concavity change. We're going to say that since f double prime is what we're looking at it, that means on the interval from 0 to 2, the graph is concave up. Now remember, we're talking about the graph of f, capital F. So on the interval from 0 to 2, the graph of capital F is concave up. The graph of capital F is concave down from 2 to 4. And then from 4 to infinity, the graph will be concave up again. So now we're going to apply 1 through 5 to draw our graph. So we know that we have mins and maxes, a local min and a local max. We know that we have, wait, gotta go right back down. And we have to say one more thing in the end. We know we have inflection points. Boy, if that doesn't drive you crazy. We know since the concavity changes, we have a point of inflection at 2, and we have a point of inflection at 4 as well. So we're going to try to draw this graph now, going back up, and let's apply the information. We know that when we start off, we know that our slope is negative because it's underneath, our graph of f is underneath the function. Maybe I should actually pull it so you can see both graphs. So if I pull it, so you see both graphs there, and there we go. Okay, so now referring to the original graph, I'm in blue, right? Okay, so I start at 0, 2. That is the first. Remember, this is the graph of capital F of x down here. So now we're going to start at 2. Now we decrease, the function is decreasing until it gets to 1. So I'm going to make it easier myself. I'm going to say, okay, it's decreasing until it gets to 1, put a point. This is going to be a minimum on f. In fact, it's a local minimum on f. Then after it gets to 1, it's increasing. And all the while on this interval from 1, 2, 3, 4, 5, watch the concavity as well. So I'm going to go from a minimum to 2. The graph is concave up on the interval from 0 to 2. That matches it. But at 2, I have a POI here, point of inflection. And then from 2 to 3, the function is increasing. So it's increasing from 1 to 3. Just taking a look at this from 1 to 3. The function f of x is increasing. And then after 3, we have a local maximum at 3. We have a local maximum at 3. Then the function decreases. And then you have a point of inflection at 4. I'll put it right here. So decreases, you have concave down, and then it changes to concave up again after 4. And then the slope, remember, the limit as x approaches infinity, as I continue this, it gets flatter and flatter. So we have a point of inflection where the graph goes from concave up to concave down that matches what we're talking about. So here's my concave up interval, my concave down interval, and then I have a concave up interval as well. So that does it for us. We have the entire graph drawn where it's decreasing on the first interval, then it's increasing, and then it's decreasing, still decreasing all the way from 3 to infinity, but then you see your changes in concavity with your points of inflection. Okay, that's it for that problem. Pause at different parts in case you need clarification. Again, there's the end of it. Okay, and let's see what we have. On this one, we're going to look at slope fields or directional fields on number 6. So some of the values, I'll give them to you because they can take a little bit of time, some of the values for the slope that we find. But essentially what we're going to be doing is looking at what we call a direction field. So I'm going to write this right here, and you'll see where the direction field has to do with the slope of the antiderivative. So if the function that you see, the function, if f of x is equal to that function, sketch the graph of the antiderivative. Ooh, this is what we have to sketch. So we want to sketch the graph of the antiderivative, capital F. It satisfies the initial condition, capital F of -1 is equal to 0. So the point on the antiderivative, the first thing I would say about, you know what, I'm just going to, since I want to sketch the graph of the antiderivative, and I'm going to use a direction field, I'm going to say I'm going to plot this point. So I'm going to plot the point -1, 0. Okay, so put that on the graph. I'm going to scroll a little bit. -1, 0. -1, 0. So that's our initial condition. Almost put 0, -1, -1, 0. Okay, now what we're going to do is we're going to look at the slope at each value of x. So recall that, the second thing I'm going to look at, oops, pen, 2. Recall that f is equal to capital F prime, and we're going to use that. So if we know that f, this function up here, is the slope of our antiderivative, then we can use that. So if we look at f of 0, in this case, if we do the calculations for this, the slope will equal 1. I'll leave that to you to plug into this function where we put 0, 0, 0. Okay, I'll leave that up to you. And let me undo those now. So we have f of 0 is equal to 1. So we know at x is equal to 0, slope is always 1. So that means that f prime is equal to 1. So now I'm going to put these in a table in a minute. So then I have f of, let's look at it, one more value, f of -1. As it turns out, when you plug that in, you're also going to get f of -1 is equal to 1. And that's at x is equal to -1. Now, if you recall, I talked about antiderivatives belonging to a family of functions. So what we're going to do is we're going to show slope, little tangent segments at x is equal to 0, and then at x is equal to -1. So you can see we're going to be drawing what is called a direction field. So at x is equal to 0, you have to kind of figure where you're going to put things here. And I'm looking at this point at, these are points that are not part of the graph, but I'm going to put little tangent segments on these points, and I'm going to use them to guide my slope. Let me undo here just for a second. So when x is 0, I'm going to go up the y-axis, and I'm going to say, okay, slope is 1. So that's a slope of 1. That's a slope of 1. That's about a slope of 1. And really a game of estimates here because it doesn't have to be exact. Then at -1, I'm also going to do the same thing. There's a slope of 1. There's a slope of 1. 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 Now, I could continue to do this, however, with f of 0.5, f of -0.5, and so on to get values. But instead of doing that, I'm going to give you a table of values, and we'll just put the values in. So in the table of values, and we did this in chapter 2 when we were looking at slope. We're going to do a table of values where x is the x value, and the y value is going to be capital F prime, or the slope that we get. So we already got 2. Remember that this is f prime of 0, and this is capital F prime of -1. And all of the slopes at all those places, I'm missing one down here, is 1. Now, In a table then, I'm going to put the other values. So I'm going to put all of them. -1, the slope was 1. -0.5, the slope is, I get 1.4. And I'm rounding to the nearest tenth. Takes up less space. So at 0, the slope is 1. And at 0.5, the slope is 0. I'm going to make it just rounded to the tenths. I'll say 0.6. And then at 1, the slope is 0.4. So they're pretty close. And they're going to look very similar when we draw little tangent segments. And then at 1.5, the slope is 0.6. And then at 2, the slope is 1 again. And at 2.5, the slope is 1.6, getting steeper. And then the last one at 3 is 2.3. Straighten out my work here. Can you just erase those little scragglers? Okay, so there's my table of values. So what I'm going to do is include those in a slope, in the slope field as my little segments. So let's go to -0.5, and we have a slope of 1.4. So I'm just going to make it a little bit steeper. And you might say, oh, that doesn't look like it's a little, yes, it does look a little steeper, but like that, okay? Just a little bit steeper. It might even look like a slope of 2, but for the purposes of what we're doing, it doesn't really matter. So now I'm going to go to 0.5. So at 0.5, the slope is 0.6. So remember, 0.6 is 6/10, a little more than a half. So if we look at it, if we go from -1, a rise of 1, and a run of 2, that would be a slope of 0.5. So I'm going to make it pretty similar to that. I'm going to say from here, I'm going to shoot to 2.5. So like that, like that, like that, like that, and like that. Those two look, this one looks a little bit too steep, so I'm going to make it a little bit less shallow. Okay, so we have those in. At 1, then the slope is 0.4. So now it's a little less, so it's got to be a little more shallow. So looks like it goes a little flatter. And then at 1.5, it's 0.6. 1.5 is 0.6, so it gets a little steeper again. Not too much, though. And then at 2, it's 1 again. So now, again, I'm going to use the points on the graph. So I'm going to go like that because it's pointing upward to that point and upward. And I just make it a real tiny segment. Okay. And then at 2.5, it's 1.6. So I'm going to make that a little bit steeper. Yeah, a little steeper than that. And see, I could do a lot of points. I got 2.3 here now, so a little steeper still. Okay, so now, when we draw the graph, you can see there's kind of a wave going on here. And yet sometimes it's very difficult to see just exactly what's happening. And here's what's going to happen. We're going to start down at the bottom at this point, and we're going to come up at 1, and then we're going to follow like it's a river. If you kind of follow like it's a river. Okay, now I'm going to stand back from that because I'm not really liking what I've got here, so I'm going to change it just a little bit. So I'm going to attempt something different. I'm going to say, okay, yeah, there we go. There, now I've got the flow. Okay, so for our antiderivative, now this is a rough sketch of what it would look like, but picture this, that we could follow the flow like a family of graphs. It's yellow, green. Let's go green. So the same thing could happen. Oops, wait, slid off of that one. Okay, so if I have a function up here, that this could represent a family of functions with the antiderivative family of functions. Okay, so now this yellow graph, let me just complete this. This yellow graph, and really the blue and the green, of an f of x is in the family of an antiderivative, f of x, is in the family of functions capital F of x plus c, which are all vertical translations of one another. So something that you were used to in Algebra 2 and Honors Pre-Calc as well. So just something to think about. In the AP, we call this direction field, we call it slope fields, and it's a topic that we'll have a whole unit on involving differential equations. So let's try one more problem before I give it up for the night. So a car is traveling at 50 miles per hour when the brakes are fully applied, producing a constant deceleration of 22 feet per second. What is the distance covered before the car comes to a stop? In this problem, when you think about the car coming to a stop, this is putting the brakes on, screeching, and how far does the car travel at that point? So I take the information, I go, okay, well, I'm just gonna go like I normally do in a word problem, start making a list of information. So I have, it looks like v of 0 at the beginning is equal to 50 miles per hour. And then I take note that, oh, we have 22 feet per second squared. I know that's acceleration, but I might want to change the 50 miles per hour to, I'm going to multiply by 5,280 feet over 1 mile. Miles are going to cancel. And then I'm going to multiply by 1 hour over 3,600 seconds to get the units that I need. And that would turn out to be v of 0. The initial speed then is 220 over 3 feet per second. Okay, so then I also note, as I'm reading along, I have this 22 feet per second. So I know that, that gives me a of t as a constant, which is negative 22 feet per second squared. Now, the thing about slowing down, if you're slowing down velocity, let's take the direction of the Jetta. Aren't they cool? So I've got velocity maybe going this way, velocity, and it doesn't matter whether it's left or right, you set the orientation. But if I'm going 50 and acceleration is slowing me down, it's decelerating, then velocity and acceleration are moving in two different directions. So acceleration is negative. So we start off, we have a of t, okay? And then the problem says, what is the distance covered? So let me take one more thing. What I'm looking at, this is kind of my list of stuff as I start a problem. And then I'm going to say, okay, we are looking for, the question is asking, what is S final minus S initial? In other words, how far initial? How far have you gone? Okay, so I don't know what time it is when you finish, so I'm going to just call it T star. It's going to be some time, but I do know the time of an initial study, so to speak, and that would be T is equal to 0. Kind of like I have up here, you know, at T is equal to 0, I know that the velocity is 50 miles per hour. Okay, so I'm going to box this up in case I need to glance back up, and we'll see that information. And what are we looking for? So that information. So we're going to start with our acceleration. We start with a of t is equal to negative 22 feet per second squared. And then we're going to find v of t. So there's my a of t, then I find v of t. I'm going to get my velocity. So that's equal to negative 22t plus c, an arbitrary constant. Now we know that the velocity is 220 over 3 feet per second when time t is equal to 0. So the first thing I'm going to do here is I'm going to solve for c. So I get c is equal to 220 over 3. Box that up. And then I'm going to write my velocity equation. I have v of t then is equal to negative 22t plus 220 over 3. Okay, let me pause for a minute. Okay, so it's pretty cool. We have our velocity equation. I'll put that in yellow. It's our caution yellow. Okay, now 3. So I got my velocity equation. Now for the third part, I might want to stop and reread the question. For the third part, so what about this when the car stops? Let's get that information because it says a car is traveling at 50 miles per hour when the brakes are fully applied, producing a constant deceleration. So what is the distance covered before the car comes to a stop? If you noticed in my what do we need to know question, or what do I need to know box here, I want to know what is the distance traveled. I don't have the time, but I do know something about this. I know that when the car stops, when car stops, I know that V is equal to 0. V of t, is equal to 0. So when the car stops, V of t is equal to 0. That helps me because then I know 0 is equal to negative 22t plus 220 over 3. And then I can solve for t, and you can easily see that we get t is equal to 10 thirds second, or 3 and 1/3, but I prefer 10 thirds. Okay, 10 thirds seconds. Well, how is that going to help us? Well, if we know 10 thirds seconds, then we know up at the top, we know we need S of 10 thirds minus S of 0. So I'm going to put that there for, I got to scroll the right way here. 3, 4, we'll put 4 here, and then we'll start to, let's go over this way. So for number 4, let's come up here. So we know we want S of 10 thirds, because that's the time the car stops, minus S of 0. So we stand to reason we need S of t. So we need to find what S of t is. So you have V of t. Let me scroll a little bit up so you can see V of t there. So we have S of t is equal to negative 22t squared over 2 plus 220 over 3t plus, let's use another constant, d. Can we use d? Can we use d? Do we need e? Let's use d. Okay, so we have S of t, or do we? Not yet, because we have a d in the mix. If we put 10 thirds in for t, then we're going to still be stuck with another variable, d, or a literal constant. So we need to conclude something else now. We know what S of 0 is. S of 0 is equal to 0. So if I plug in, and that's the initial distance, because remember, that's the start of this whole enchilada. So we've got 0 is equal to 0. The first term is going to be 0. The second term is going to be 0. So we know that d is equal to 0, because you just get 0 plus d is equal to 0. Therefore, d is equal to 0. So now we know S of t. So we know S of t is equal to negative 11. I'm just going to simplify that first term. T squared plus 220 over 3t. That's our function. So for lucky number 7, then we are going to find S of 10 thirds. So it's negative 11 times 10 thirds squared. What if I said no calculators? All right, no calculators. Just kidding. So 10 thirds, okay? So we have number 7. That's where we're finding S of 10 thirds. Remember, in the end, we want the difference from S final to S final minus S initial. So we get, when you simplify this, I'm sure you can work this out and double check me on this, 122.2 feet. So Remember, this is a car that's probably going in a straight line. You're talking about linear velocity again. So for number 8, to finish this off, the grand finale, the whole enchilada, we have S of final minus S initial is S of 10/3 minus S of 0, which is 122.2 minus 0, or 122.2 feet. This is the distance. Go the distance. This is the distance the car traveled after the brakes were applied. And how about if I just leave the car traveled? Now there's one more mastery problem. I'm not sure I have enough time in the video to get this done. So you can do it yourself. It's actually, I just want to tell you to change this on your notes. It's actually number 33 from page 305 in your book. So if you want to try that, let me delete this. Such the perfectionist. So let me tell you what I got for an answer, and you can double check. This, you should get f of x is equal to x squared minus 2x cubed plus 9x plus 9. Okay? And good luck, and I will see you tomorrow.